from a colleague of mine. I think she teaches in Florida now, um, on Gauss's law, which I thought were really good. So, big idea, and this is kind of like the flux. When we talked about magnetic flux, basically is passing through an area. Now, normally we'll talk about it being an enclosed area, but this is a good visual. So if we have arrows passing through a surface, we're looking at the total number of arrows passing through an area, and that would be the total electric flux or flow. Normally, again, we would have things being um, enclosed. So the electric field vector is this labeled by this A, and this is the area here, and these are the arrows. So that's why it's really a dot product. If you look at formula E3 on your formula sheet, it's the surface integral of E dot dA equals charge enclosed divided by vacuum permittivity. The reason it's a dot product is this is the area vector. It's kind of weird. That's all that means. What's weird is they use the same symbol for a line integral, which they talk about with magnetic flux, which is weird. So total number of field lines. So I've got 3 coming out, 3 going in, net flux of 0. Here, 3 coming out, 1 going in, the net flux would be 2 without any weird units or stuff like that. So when they pass out, flux is positive. When they come in, it's negative. Flux of this symbol is 0. So that says there's no charges in here. So no positives or negatives. However many field lines come in, which is 1, 2, 3, are the field lines that come out. 1, 2, 3. This is kind of weird with, it says a spring. You can't really even see the water there. So this just is really the sum of charges within a surface. A closed surface is equal to the flux. But it's the sum of the charges divided by vacuum permittivity, which give you our units for flux. Yeah, so this is kind of important. You should never have to evaluate a surface integral. It's either E times A, which equals charge enclosed divided by vacuum permittivity, or it's going to be a 0. And chapter 27 really thought about symmetry a lot. So that equals electric flux, and that equals electric flux. And that's how it's shown in formula E3. Technically, both these would equal electric flux. Notice again, this is E equals KQ over R squared. That's the equation for electric field for a point charge. Why? Because area of a surface of a sphere is 4 pi r squared. It's kind of funny how Faraday thought about that. It's a nice face. So this goes through basically a cylinder of charge. I talk about that also in my other video. So I think this does a nice job of explaining why and using the variables. Yeah, that's the one I was talking about, sigma, which is basically the charge density in terms of area, charge per area. Going to skip over that. This is a nice summary here. Really, we're worried about this, maybe a little bit about this or this. This is the key aspect. You want to really remember that general idea. And that's it.